Hello, my name is Jeff Passmore. I work for JDSU's Sales Support Organization. I'll be your host today on the first presentation covering the basic copper measurements on the HST. When I was a young fella first starting out at the phone company, I was taught a series of measurements to make on a cable pair to diagnose it. And that series of measurements was based on the fact I used an analog voltometer because that's what they gave me. The first thing I was taught to do was to check the cable pair to see if it had cross battery on it first. If there was no cross battery, to next check it for shorts and grounds. If there were no shorts and grounds, to kick it, see how far it went. So those are the three basic things we're going to cover first on the HST. So my voltmeter is found under option number 1, DVOM. Now, there's two ways to start that. I can highlight it and press OK. And I can also reach down here and press the digit 1 on the keypad dialer. They both accomplish the same thing. When the HST has been turned off, you turn it on and go into DVOM. This is the first thing you're going to see. It is a voltage snapshot measurement for both AC and DC battery. Like all modern meters, we auto range and auto scale, so you never have to worry about a range or a scale. We even move the leads around for you. All you got to do is hook it up and push the button. All right. I made 6 measurements there. I made them relatively quickly. On the surface, this appears very attractive. Well, anytime I see something that looks good, the telephone person in me comes out and I automatically start looking for the bad associated with it. Well, I don't know if this is necessarily bad, but it is a voltage snapshot. What I mean by that is it's a picture in time. So if I hooked up dial tone to my tip and ring leads right now, I would still show 0 volts DC until I did another snapshot. Most phone technicians don't like that. They like to view things continuously or in real time to monitor for changes. Well, if you look down at the bottom right-hand corner of the screen, the word continuous appears above F4. So if I press the F4 key, it'll take the first of that list of 6 and display it continuously. I tell each session that it's worthy of taking a nice, slow, long look at this opening screen because if we understand this screen and its operation, we're going to automatically understand 3 or 4 additional screens because their layout are the same. First of all, I tell you what I'm measuring across the top, AC volts tip to ring. In the upper left-hand quadrant of the screen, I show you the 3 possible lead combination. I bold out the active one and I gray out the 2 inactive. In the upper right-hand quadrant, I even show you what colors I'm looking across. In the middle, I give you a result. I tell people I'm not getting any younger, but I don't have any trouble reading that font size. Nice, easy size to see. And then at the bottom, I do something called lowest and highest. What lowest and highest does is keep track of the measurement over time. Why that's important is when I was using an analog voltmeter or even modern digital voltmeters, most of them read real time or continuous like this. But if you're monitoring a measurement to see whether or not that value is going to go up or down or it's going to change or the trouble is going to appear, right? You're pretty much forced to stare at the instrument, right? If you take your eyes off it and a change appears, you've just missed it. Well, lowest and highest will let you take your eyes off because any change in the result will be captured down here under lowest and highest. Up towards the top, in admittedly small font or letters, are 2 incomplete sentences. The first one says left-right changes the cable pair. Well, that's referring to the left and right arrows. So if I press right arrow once, you'll see it change the lead combination, right? So it's gone from tip to ring, or to ring to ground. Hit it again, it moves to tip to ground. Hit it a third time, it just wraps right back around on itself and goes to tip to ring. Right? So that's how I move the test lead. Now what can I do with an AC volts measurement? in keeping with my promise of what's in it for me for each one of these measurements, I'm now going to switch to my whiteboard. When you say AC voltage to telephone technicians, usually their first thought is electrical shock, right? I'm going to get a poke. Well, I don't know about you folks, but anytime I received a good shock or electrical poke from a cable pair, it was in the process of hooking up the test leads, right? Prior to any voltage test getting a chance to run. That's when I got shocked. Yeah. Well, aside from shock, what can I do with an AC volts measurement? Well, if you and I were out on measuring a dead cable pair to the field and we saw AC volts tip to ground of, say, 2, and we saw ring to ground of, say, 4, I asked my live training classes, was that a good or a bad thing? This is AC volts, right? Obviously in a recorded session, you can't answer me, so I'll answer for us. It's a bad thing. When the AC voltage gets put on the cable pair by the power company, just as much is put on tip as on ring. There is no discrimination there. Therefore, if we see a difference between AC voltage, tip to ground, ring to ground, we automatically know there's some form of difference between the two wires. The only difference in tip and ring in our world is a bad thing. So we would look at that and I would say, well, I don't know what's the matter with it, but I do know it's in trouble. Right? So you can actually think of that AC volts red to ground as a crude indication of pair balance. What else can I do? Well, where I worked, we had long rural loops. Every so often we get a customer that would complain of partial rings. Line ring short is what we called it. But you'd go out there and there'd be no short on the line. The only other application I can think of for AC voltage is to use your AC voltmeter, hook it across tip and ring, and ring the phone back. Now, I'm not a central office guy, but they tell me at least 85 volts should be coming to the phone when it's ringing. So even in your more populated areas, your remotes and your slick cuts, they have ring supply generators in them, and they do go bad from time to time. So those are the two practical things I can think of for AC volts. I am now going to go back to my HST. The second little incomplete sentence up there towards the top says up and down changes the test. Well, again, it's referring to the arrow keys, so let's try down arrow once. We'll see the meter went from AC volts to DC volts. The screen looks identical, and it operates identically. So left and right is going to change the lead combination. All right. Lowest and highest, hopefully that's making a little more sense. If I thought I had a swinging ring cross, I could hook my HST up ring to ground continuous DC, set the meter up on the cross box, walk back to the truck, get my coffee, come back and would not have missed anything, right? Because lowest and highest would have captured it. Yeah, kind of a simple example, but a practical one. Press F1, the display button. Underneath F1, there is an option for a POTS dialer. Well, a lot of technicians don't even know the dialer is there, but of those that do, I would say about half of them use it. Because what you can do with the POTS dialer is pre-program numbers into the HST and let the HST dial them for you. Right? Common example of that would be a drop battery number. Right? Well, of the half that knows the dialer's in there that do not use the dialer, they'll say things to me like, well, you know what, Jeff, I've been using my butt set for 20 years. I think I'm going to stick with that. Well, that's fine with me. Either way is okay with me. I just want to make sure you know the feature is there. Press F2, the Actions button. Underneath Actions, there's an interesting setting. On mine, it's labeled 4 and 5, and it refers to something called 1 mega ohm term and 100 k ohm term. I like to discuss this and describe what it means. It's important for a couple of reasons. Primarily, though, it's a great example of the things that I used to stare at on test sets and did not have a clue on what they meant. All right? type of terminology I saw in a lot of things. I didn't know what it meant. I asked around, it didn't seem like anybody else knew either. Well, as I said, I don't know if you know or you don't know. If you don't know, you're going to find out because it is worthy of your attention. So I'm going to switch back over to my whiteboard. When we have a crossed cable pair, we know we have the ring conductor from one pair touching either tip or ring of our pair, right, through some form of a fault. So I'm drawing two cable pairs here. A cross would be the ring conductor from this pair touching either tip or ring of our pair through some form of a fault. If it's a Potts line, we know how much battery is involved, right? It's 52 volts. Well, this circuit's a lot easier to look at if you erase the unnecessary lines, because all you really end up with is a simple series circuit with a resistor in it. The resistor being the place where the two wires are touching one another. So that's what I had up there a minute ago. I just erased the unnecessary lines. A lot of technicians are surprised to find out when you measure DC battery or measure for cross battery, your meter has an internal resistor built into it called a termination. So really the circuit we're looking at is that series circuit with two resistors in it. Well, we're going to talk about a quick rule of electricity. Don't worry, there's no math involved. In over 20 years of doing this, I've never had anyone fail to get the rule yet, so it's not complicated. First of all, I'm going to change the 52 to 10, just because the rule's a little bit easier to understand with a nice round low value like 10. Resistance is measured in ohms, right? Well, let's give these two resistors ohm values. Let's say this one is 5 ohms, and let's say this one is also 5 ohms. The rule goes like this. If I measure and do voltage drop across the resistor in a series circuit, meaning how much of that 10 volts will show up across this 5 ohms, when I add it to whatever shows up across this 5 ohms, their total has to equal 10. That's the rule. It's hard and fast. It's like Ohm's law, right? About the time you think it's wrong, just means you made a mistake. Well, even if you've never heard any of this mumbo jumbo before, would it make sense to you that, heck, whatever I see across this 5 ohms, I'll probably see the same thing across this 5 ohms. They're both 5 ohms. Well, that would be a logical and a correct assumption. 5 of the 10 volts would show up here, and the other 5 would show up here, because added together, they have to equal 10. Now, an interesting thing happens with the rule when you start playing around with the values of the resistors. We're going to leave the one on the right at 5 ohms, but we're going to change the one on the left to one of your meter settings, 100,000 ohms. Right? Now, the rule still works the same. This is 100K, right? K meaning 1,000. So 100,000 ohms over here and 5 ohms on the right. The rule still works the same for voltage drop across the resistor. The interesting thing is this. Next to nothing shows up across this low resistor, and almost all of the 10 volts shows up across the higher resistor. All right. Jeff, you're beginning to bore me a little bit with this. Let's get back to telephone stuff. Alrighty, we're going to do that. You and I are going to measure 3 cable pairs. You're going to measure them first, and we're going to discover why it's important to have understanding of this rule. When I talked about cross cable pairs outside, I rated them, right, based on the amount of battery I saw. So I would say this one's got a hard cross, this one's got a medium cross, this one's got a light cross, things like that. Well, pair 1 has got a hard cross. The actual value of the resistor, or resistance of the fault, is only 5 ohms. Your meter is set to 100K ohm. Well, if you got 5 ohms on the right and 100,000 ohms on the left, most of the battery is going to show up across your meter, right? Just like our previous example. So pair 1 is going to show you maybe 51 volts. You'll say, boy, that sucker is crossed. Well, now we measure pair 2. Instead of having a hard cross, we have a wet cross. The actual cross value happens to be 100,000 ohms, the same as the termination of your meter. Well, if I got 100,000 ohms on one side, 100,000 ohms on the other, the 52 volts has to split. And in that case, pair 2 will show me roughly 26 volts. Finally, we measure pair 3. This is the type I worked on as a cable maintenance guy. This one is a damp cross. The actual cross value is 1 mega ohm, mega meaning million. So I got 1,000,000 ohms on the right. I only have 100,000 on the left. In that case, most of the 52 volts is going to show up across the fault. Very little shows up across the meter. I walk up. I say, hey, what are you doing? You say to me, well, the boss has been after me to use this new HST meter, so I'm just sitting here measuring cross battery. I know this is a section of bad cable here, so when I go in tonight, I can tell him I used it. Well, I tell you, he's sort of been after me to do the same thing. Could I tell him that I measure the same pairs that you, so I can tell him I use it as well? And you say, sure, go ahead. Well, unbeknownst to both of us, because no one ever took the time to explain it, my HST has the check mark next to 1 mega ohm. So I read pair 1, 5 ohms on the right, 1,000,000 ohms at the meter. Just like your meter, most of the cross battery shows up at the meter. I measure pair 2. I got 100,000 ohms on the right, but I've got 1,000,000 at the meter. Unlike your meter, most of the battery shows up at my meter. Here's where you and I begin to see our first difference, right? And kind of look at each other and say, well, this is wet cable, things are moving around. Finally, I measure pair 3. I got 1,000,000 ohms over here. I've got 1,000,000 ohms at my meter. In that case, my cross battery will split. My HST will show 26 volts across. Your HST showed 4. We look at each other, shake our heads, and laugh and say, gosh, these purple meters can't even read battery right. Sort of a long, dry explanation, I know that, but an important one. Because you have other things in the field that read battery levels for you. For example, automated test systems. If I had a quarter for every time I heard a technician say they distrusted the automatic test systems in the central office, I would be long retired. If you question a technician about this mistrust, inevitably they will come back to cross battery. They will say the darn thing tells me I got cross battery when I don't. Right? Well, chances are it's not lying to you. It's just you're looking at a difference between input impedance termination. So back to my HST. Where should I put the setting, Jeff? Well, I don't really care. Neither one is right or wrong. They're just different, right? If you have a new modern digital meter, I would suggest you probably put it next to number 4, the 1 mega ohm term, as most of the modern meters come at a high input impedance termination. But neither one is right or wrong. Well, you may ask yourself, why'd you put selection in there in the first place? Just to confuse us? Nope. Some phone companies want their lines measured at 100 k ohms. Others want them measured at 1 meg. Now that you know the difference, it's really no big deal. So simply highlight your selection, press OK, and you will have set the input impedance for your meter. All right, that concludes our first segment on voltage, AC and DC. We thank you for joining us and hope you will join us for session number 2 when we'll begin to discuss current and resistance. Thank you for attending.